Let us begin then. Okay, so what have we been studying? We've been studying Taylor polynomials, and we said a few things about why they're important, but we've really only done a little bit of that, so we kind of need to take it a step further. So why do we study Taylor polynomials? That was the purpose of the last few classes. And so we made a few observations. If we're just speaking sort of in a non-complete manner, the general idea is that they're very good at approximating functions. That's essentially the point we were trying to make, that given a function which might have a very difficult description, or it might be difficult to work with using derivatives or integration, what the Taylor polynomials are is they are a way of approximating, quote unquote, a function with polynomials. And then we talked about this notion of how accurate is our approximation, and I said how we're not going to get into that in this particular class per se, but we will hit a little bit on that soon enough. Our goal now is to go a step further and I alluded to this at the end of class. What happens to p sub n of x, this Taylor polynomial, if we let n go to infinity? I mean, this is a natural question if you are thinking about the graphical representation of what we were doing. We were taking these functions and we were graphing them, and then we were graphing them on the same axes as a Taylor polynomial. And as we increased the degree of that polynomial, what we saw in our examples at least is that, say, the Taylor polynomials began to go right on top, as you might say, of the graph. So what that tells our mind is if we keep going to degree 8, to degree 100, to degree 8,000, that at some point the Taylor polynomial of degree 10,000 should be indistinguishable from the actual function. At least that's what our intuition tells us. That's what the graphics tell us. And even if we did some analysis, it would tell us the same thing. And so we want to take advantage of that. We'd like to investigate that more. So what we're going to do then is we're going to study a more general type of scenario. So let's put this into some language. So the standard way we answer this is we study a new object. And this thing is called a power series. So again, let's make sure we're on the same page here, because this is it might seem like we're jumping around, but if we think about what a Taylor polynomial is, a Taylor polynomial is a polynomial. It is of degree n, whatever degree we decide it to be. Is it 4? Is it 6, 7, 8, 9, 10, 47, 257 degree, whatever degree you want. And so in many ways, a Taylor polynomial, if we pretend this idea of sending n to infinity, a Taylor polynomial sort of becomes what we're going to eventually call a Taylor series. That is, it is a series. So let me explain what I mean by that. So a power series is a series of the form this. Now I'm going to write it out in its scary form first. So this looks scary, but let's just think about what this looks like. So if we write this out, what is a power series? A power series this is for all lack of specific words, this is a polynomial of infinite degree. So what do I mean by that? Well, if you start, what is a polynomial? Polynomial is a number times a variable to a power. Well, that's what we have here. We have a number c sub 0, a number c sub 1, c sub 2, c sub 3, times a variable raised to a power. And the subscripts are only there to associate which constant, or, we call these coefficients, as you're aware. So let's make sure we're cool with that. These are the coefficients. Just like we called, if we had a polynomial, we called the numbers coefficients. So before we go any further, let's ask ourselves, why would we study these? Well, let's recall P sub n. Our Taylor polynomial looks like this. It was actually f of, say, 0 plus f prime evaluated at 0 times x plus f double prime evaluated at 0 over 2 factorial. Oh, forgot the x squared here. So this guy looks like this. So thus, if instead of stopping at n, so if we don't quote unquote stop at some n, we obtain a power series. So a Taylor polynomial can be written, instead of stopping at some fixed number n, so if instead of saying we're going to stop at n, but if we just let this thing go, we create a series, and it is an example of a power series. Why is that? Because even though these numbers look frightening, these derivatives divided by these things with factorials, they look frightening. Those are just numbers. So in order not to scare the heck out of you, let's just look at an example. So one plus x plus 1/2 x squared plus 1/3 factorial x cubed plus blah, blah, blah. If I don't stop, this is a power series. If I take x minus 1/3 factorial x cubed plus 1/5 factorial x to the 5th minus 1/7 factorial x to the 7th, this guy, if I continue forever and ever, is a power series. So the point I'm trying to make is that there's some connection out there with Taylor polynomials and power series. So that's why we're going to study them. I don't know if that makes sense. Maybe I hope I'm being clear. I'm not sure. Let's kind of tie this up with the following. Moral. There is some connection with Taylor polynomials and power series. I haven't told you what the connection is yet, but maybe you can start to see the writing on the wall. Does anybody have a question, comment?
Will the power series always be noted in like ascending order for the variable?
Yeah, that's typically like why you do it, because it's never ending, right? So if you try to write it the other way, how could you write it in descending order? There's no largest power. It's actually always increasing. That's what the ellipse is. The dot, dot, dot here and here telling us that this pattern continues forever. It never ends.
Okay.
Yeah. So it would be impossible for you to write it in a descending order. Now, if you had a Taylor polynomial, for sure you can write it in descending order. But that gives you a good reason, the foreshadowing. If you think about any time you read about Taylor polynomials, how is it always written? It's always written in ascending order. And the reason for that is because if we want to continue it, if we don't want to stop it at some fixed power, if we want it to go forever, well, then the only way we could write it is in ascending order. Does that make sense?
Yeah.
Yeah. Well, I notice when I like lean in, my head gets this light glare on it, looks like. Oh, isn't this fun? Okay. So power series seem to be in many ways, and we're going to find this out, they are like a special case of a Taylor, they're a more general idea than a Taylor polynomial. And if you haven't guessed it already, we're going to have what's called a Taylor series. We just haven't defined that yet. What we need to do now is we need to first understand that there is a good reason, we have good motive for studying power series, and that is that they're somehow connected with these Taylor polynomials. So that's what we want to do right now. So that's what we're going to do. So let's talk about some notation first. So we can define a power series centered at a particular value A. So what is the power series in general? It looks like this. And this is, again, very similar to what we talked about with our Taylor polynomials. So let's write out the first few terms. When k is 0, you get just a number. We'll call it c sub 0. When k is 1, you get a number. We'll call c sub 1, and it's times x minus a to the power 1. When k is 2, you get a number times x minus a to the power 2. And of course, this pattern continues forever and ever and ever. So there's two ways to study this. We could study it centered at A, or we can study it centered at 0. It doesn't matter, because what is one of the things we learned about when we were in an algebra class many, many years ago? One of the things you learned in an algebra class or a pre-calculus course is that you can shift a function left and right. How do you shift it left and right? You have to compose it with x minus a, and that either shifts it left a or right a. That's one of the things you talked about in an algebra course, shifting a graph left and right. You also did up and down. So basically, the way to think about this is there's no reason to make things more ugly in notation with studying it centered at A, because we can always just do whatever we want centered at 0, and all those facts sort of can be applied to us centering it anywhere. So let's just remind you this. This is centered at A. And then if A equals 0, it just looks like this. So this doesn't look as sort of as aesthetically scary as the one above it. Now, it turns out, even though these things are very complicated to state, it looks, and they're not complicated to state, but let's not lie to each other. When someone in a Calculus 2 course looks at what's written on this board right now, you're overwhelmed. It's these scary symbols. Everything just seems so arbitrary. And I understand that. I felt the same way. But if you keep in your mind, sometimes it might be useful for you to put your hand and cover up. I know you can't see what I'm doing, but cover up the sign, the big sigma, and just look at the polynomial aspect of it. It's just a polynomial that never ends. So you can really think about it as a polynomial of infinite degree. That's all it is. It's a number plus a number times x plus a number times x squared plus a number times x cubed plus a number times x to the 4th, etc., etc., etc. Okay, so what's the big question? Well, if we paid any attention to the last sort of handful of classes before we talked about the Taylor polynomial, we had a very, very big, important question. For what values of x will the power series converge? So that's just the first thing. If I tell you we're going to study a series, the first thing you would want to think of, does this series converge or diverge? How and why? But if we look at a power series could converge, it could diverge, and that might depend particularly on what is the given value of x. You know, in a power series, and again, this goes back to the context here. When we write a letter like x or y or t, unless otherwise stated, you're supposed to assume that is a variable. And when we write letters like A, B, and C, unless otherwise stated, you as a student and as a student of math are supposed to assume that that number is a fixed constant. So when I look at my power series, if I go back to the previous page, if I look at my power series, we are supposed to assume that x is a variable, can be any number at once. And we are supposed to assume that these coefficients, C0, C1, C2, are fixed constants. So luckily, there's a very powerful theorem about this. So we have a very nice answer to this. And it's a big theorem, but it's easy to state. And it's very easy to use. It turns out that our friend, the ratio test, is going to be a very, very, very important sort of member of our toolbox right now. Theorem. Now we're going to state this for the case A equals 0, but you can state it. The result holds centered anywhere, but it's just easier to state. It's cleaner. So let's consider this power series, c sub k x to the power k, which of course is c sub 0 plus c sub 1x plus c sub 2x squared. So there are 3 scenarios. So there's 3 things that can happen. It has to satisfy the first, the second, or the third. It cannot do 2 or more. There's 3 scenarios. 1 must be true, the other 2 must be false. So let's imagine, and let's list these things in a hierarchy of what we would love. Let's assume that we like convergence and we dislike divergence, right? Maybe you're the opposite, I don't know. But typically for most things in a calculus course, convergence is a nice property to have. We would prefer series that converge. Not always, but often. All right. So what is the best case scenario? The best case scenario is the series converges absolutely for all x. That is the best case scenario. The best case scenario is you can plug any value in for x and it'll converge. Okay, the next best case scenario is that it doesn't converge for every x, but it does converge for some x's. And this is the best part that we can imagine how natural and stuff this works out. The next scenario is there is some number r greater than 0 such that the series converges absolutely for x between negative r and positive r. Ain't this something? So what's cool about these power series is inherent in them is some sort of symmetry. The first thing is you converge everywhere. That's the ideal situation. We get real excited for that. But if that doesn't happen, the next best case scenario is that it converges on an interval. And not only is this interval, not is it just any old interval, it is a symmetric interval. It is from negative r to r. It's completely symmetric. It's not, there's this inherent symmetry that's really beautiful about these things. And then the last scenario, which is not the best case scenario, is that the series converges only when x is equal to 0. But that's kind of like a dud case, right? Because if you replace x with 0, there's nothing to add up. There's just one term. So every power series will converge at least one number, either a or 0, depending on where it's centered at. Does anybody have a question? So there's 3 things that can happen. One of these 3 must be true. That's it. Now, this is not the class to prove this, but it's not terribly difficult to prove. We're just not going to do it. Maybe you can Google it and learn all about it. Okay. So we need some terminology. So in case 2, we call r the radius of convergence. And then we call the interval negative r to r the interval of convergence. And now there's one subtlety here that we have to take into consideration, and I'll state that in a second. So here's the subtlety. The subtlety is the theorem says nothing about r or negative r. It just says in between them. So we have to take that into consideration. You leaving, Ricky? Bye. I thought you weren't taking them. What's happening? For who? Just set that on the ground. All right, well, have fun. All right. Anyhow, pardon our interruption here. So what's the subtlety here? The caution is the following. R and negative R must be checked separately. As the theorem doesn't include them. So this is a small technicality that it's difficult to appreciate when you're a calculus student. The theorem doesn't say anything about R and negative R. It only talks about what's happening between those two numbers, which means you have to separately investigate those numbers if case 2 is the scenario that you're in. Okay. Does anybody have a question?
So it doesn't include R and negative R. And you have to check those.
That's what I wrote, Daryl. That's what I wrote.
All right. Well, I read the sentence, and then, like it said, doesn't include, and I was like, wait a second.
Yeah. Okay. So I should. Well, that's because I wrote that. Actually, I'm mad at you, and I'm over here writing ridiculousness down. Let me clarify what I'm saying, Daryl. They must be checked as the theorem doesn't include them.
Yeah.
That's all. The theorem says there's some R out there that if you're between negative R and R, you converge, but it doesn't say what happens at R or what happens at negative R. So you have to study that separately. The good news is those are the only things you have to study separately because the theorem covers everything else. Okay, so what do we want to use to study these things? Well, so typically, we use the ratio and root test to investigate power series. So let's do a typical example. It should be noted so the above theorem is also true for a power series in general. So it's just easier to, there's no reason to state it twice. We'll state it once. So let's do an example to see how this sort of works. So let's look at that. I would study this example a bunch because it turns out to be, for whatever reason, power series questions are they're great calculus test questions. And the reason they're great is because they require that you have a wide variety of knowledge. They're not just testing you on one subtle thing. They're very loaded questions because you have to understand a fair amount of calculus to correctly answer them. And you also have to be able to apply calculus. You have to have some deductive reasoning. So let's look at a typical example. So they're typically stated like this. Determine the interval of convergence. For, how about this creature? How about x minus 5 to the power k all over the square root of k. K goes from 1 to infinity. So this is going to be, we'll do this one rather slow and painstakingly, and hopefully you learn from it. And you go watch the lecture again and try to make sense of it. Pause it, do it yourself, all that fun stuff. So where would we begin? Well, the theorem tells us where to begin, even if it doesn't say do this. So the theorem says that there's one of three things that can happen. And so we would like to know which one of those things will happen. And the problem is that this series depends on what value we plug in for x. Do we plug in 0? Do we plug in 5? Do we plug in 32? Do we plug in -17? Well, that would take forever to try to do that. In fact, it would be impossible. So we need a better idea. And luckily, the ratio test gives us some conditions for convergence. So let's use the ratio test. So let's compute. So we've done this a few times. Now let's take the limit as k approaches infinity. So we're going to take the absolute value of the k plus 1 term, which is x minus 5 to the k plus 1, over the absolute value of k plus 1. And we are going to divide this by the kth term. Which looks like this. Now, I said this a handful of times last week. It's worth saying again. Every time you practice these, and some of you are like, practice? What? You start to realize that you can skip numerous steps in the ratio test. So I'm going to flip the denominator. I'm going to remember my 5th grade math. My 5th grade math says if I have a fraction over another fraction, I multiply by the reciprocal. So this becomes x minus 5 to the k plus 1 over x minus 5 to the k. And then this is times k in the square root over k plus 1 in the square root. So I'm just doing some algebra here. And then, of course, some things will cancel. This guy, this whole thing cancels with this guy. So if we go to the next page, we can rewrite this limit.
When you're finished, can you go back to the previous
Oh,
page?
yeah, I'll go back here. Sorry about that.
Okay.
Let me know when you're ready.
Okay.
Take your time. There's no award for being fast.
Okay, I'm finished.
All right, good. Anybody else? All right. I keep putting stuff in front of my page thing. All right, so if we take some time with this, we can rewrite this. This is x minus 5 in absolute values. That's all that survives. And then I'm going to write this whole thing as inside one radical. I can do that. You learned that whenever you learned your radical properties when you were a child in middle school, probably, or high school. I don't know. Now, the next thing to note is that we can also pull out this x minus 5. It doesn't depend on k. The limit is only k. So I can make this line of reasoning. And then I can also, if I need to, I can make this line of reasoning. We go back to our calculus 1. We can take the limit inside the square root. And then this limit, we now, even after last week, we explained it again, is just 1. And so this limit is just the absolute value of x minus 5. So we'll let you guys finish that up. And if you have a question about my argument, please ask. Because we're not done yet. We've only computed a limit. Now we have to interpret this limit in terms of the ratio test. All right. So what does the ratio test require? The ratio test says find this limit, which we did, but now we have to, in order for convergence, what do we need? Well, we need this limit to be less than 1. That's what the ratio test says. Go back to the ratio test. You need the limit less than 1. So we need to figure out which values of x satisfy this. Well, luckily, we learned how to solve these things before we got to calculus. This is the same as -1 less than x minus 5 less than 1, which is the same as 4 less than x less than 6. And that's exciting. So that line of reasoning just gave us a very, very important piece of information. And we're going to state that on the next page. Before I don't want to leave this page until you guys let me know if you have a question. Any questions?
Yeah, how do you get 4 and 6?
Okay, so you take this inequality, add 5 to all 3 pieces.
Oh,
What happens when you add 5 to the left side? You get 4. You add 5 in the middle, you get x by itself, and then when you take 5 and add it to 1, you get 6. Another way to think about this, and I don't know that you guys ever did, this inequality right here, this x minus 5 less than 1, what's an absolute value? You know, you could think of this in a geometric way. That means all values x that are less than 1 unit from 5. So one of the things I realize most students in math never really do is you guys don't tend to think about absolute values in terms of what they mean geometrically. They mean distance. So this inequality up here that I'm putting my pen around circling, you can think of that as asking what numbers are within 1 unit of 5. And clearly the answer are all the points between 4 and 6. So you can think of that geometrically or you can think about it algebraically. I actually wrote it out in an algebraic argument. Okay, does anybody have a question about this? Okay, so what does all of it mean? I mean, we didn't really say what it means yet. Well, it means the following. So what we can conclude is we conclude the series converges absolutely for x between 4 and 6. That's all we can conclude right now. Now, I mentioned about this theorem that we have some symmetry. We do. Note x equals 5 is the center of this series. That's one thing you should take from it. R equals 1 is the radius of convergence. Now you might say, how did you know that? Well, look at my interval. I told you there's symmetry. What is the halfway point between 4 and 6? I'll give you a hint. It starts with F and ends with E. It's 5. And then how far is it from the center of 5 to either 4 or 6? Well, it's 1 unit in this case. Now, we're not done yet, Daryl, because as you pointed out, we have to check the endpoints. So what are the endpoints? The endpoints are 4 and 6. We need to know, what does this series do when I replace x with 4, and what does it do when I replace x with 6? Those are the only two numbers I don't know. The theorem tells me if x is between them, it converges, absolutely. It tells me if x is outside of that, it diverges. So let's do that. So set x equal to 4. When you set x equal to 4, what does the series look like? Well, the series looks like this. It's 4 minus 5 to the power k over the square root of k, which is this. Negative 1 to the power k over k. Now, this guy converges. Why does it converge? It converges by the alternating series test. All right, so that's what happens when we plug x equals to 4 in. Does anybody have a question about this? Okay, so let's now plug in x equals 6. When x equals 6, you get the series 1 over the square root of k which diverges. Why does this guy diverge? Well, it diverges because it's a p-series. and the p is 1/2, which is not bigger than 1.
Why wouldn't you get some 1 to the power of k over root k?
You would, but what's anything raised to the power k? Or let me rephrase that. What's 1 raised to anything?
Yeah, 1.
Yep.
Got it.
That's actually a good question. So, because it's not always the case that that would be 1. So you do have to be careful. If that were 2, then you have to be a little more subtle, Jeff. But so it's not a bad question to ask.
Yeah, okay, I get it now,
Yeah.
thanks.
Now, if I can only spell conclusion correctly. So here's the conclusion. It's really the big hurrah. The series that we started with, which was x minus 5 to the kth power over root k, this guy converges for x less than 6 but greater than or equal to 4. So that is the interval of convergence. It's one of these half-open intervals. All right, does anybody have a question about this? Now, there's actually something we could just, there's actually something very remote, or not remotely, but something pretty sweet about this that we should, it has more to do about power series in general than this particular example. So here's a pretty cool fact. We can define a new function now. So what do I mean? Well, we can define a function. Let's call it f of x. What is f of x equal to? It's equal to this series. Now, of course, this only makes sense when x is less, when x is less than 6, but greater than or equal to 4.
Does it matter if k starts at 0 or 1?
Oh, yeah, it does matter because 0 doesn't make any sense here, first off. So that's bad news. Did I write that incorrectly on the previous? No, I didn't. Good.
No, you have 1.
Yeah, right. That doesn't make any sense. And also, this is a k, not an x. But yes, that's a good point because if I can't start at 0 here because then the first term would be 1 over, or would be divided by 0. That doesn't make any sense. Thank you for pointing that out. Okay, so this is actually, you know, something that's we take advantage of this all the time. We can represent functions as power series. Or let me rephrase it. I'm getting ahead of myself. I don't want to say it like that yet, but a power series represents a function, and then later we're going to ask the opposite question. So the beautiful thing about this now is the following. There's some powerful theorems that allow us to treat power series like they are finite creatures. They're not. They're infinite. They never end. But if we restrict ourselves to the intervals of convergence, then we can treat these things like they have 4 terms, which means we can multiply them, we can add them, subtract them, we can do whatever we'd like to do. And so we need to show you how to work with them. So it's actually quite a powerful result. More good news. So if we restrict to the interval of convergence, we can treat power series as polynomials. So things that we take for granted, like distributing and adding and subtracting, you know, they all do not create illegal things. Now, this is something that it might not make sense to you, but if I just go trying to add series together, I can make some, you know, if the series don't converge, then what I end up doing is I end up making illogical conclusions. So this is something that it might be difficult for you to quite understand, but I just can't go taking I can't just take 2 power series and add them together and expect what I get to be a power series, and even so, do I expect it to converge? And it turns out that if we restrict ourselves to the intervals of convergence, then all that stuff will happen. I also, if I have a power series, there's nothing that guarantees if I multiply it by something that what I get converges, unless we restrict to our interval of convergence. And then lastly, if we compose, there's nothing that suggests if I compose a power series with something that it should still converge. And then that's just the algebraic things that we'd want to do. What about the calculus things? What if I want to differentiate a power series? What if I want to integrate a power series? It turns out that we can do that in the intuitive way we would hope it works out, does work out, as long as we restrict ourselves to the interval of convergence. So instead of stating these theorems, let's just work with some examples, because these theorems seem very overwhelming. But you can look up the theorems in your book if you want. So the first thing we're going to do is we're going to go to an old friend and rewrite it as a power series.
Can you go back?
I can. Let me know when you guys are ready.
I'm done.
Okay, cool. So,
I got a question, Dr. O'Grady.
yeah.
So if the series converges absolutely for all x, is it still restricted? What if it's unrestricted?
Okay, so if it converges for all x, then you could do whatever you want with it. And we're going to see that. Look, I don't want to overwhelm you with all these technicalities right now. That's why I don't want to write these theorems down. But I think the question you're asking is as follows. I babbled about wanting to manipulate power series. whether I want to add them, subtract them, multiply them. And then I said we can always do that legally if the thing converges, right? And so if you already converge everywhere, then there should be no concerns. You can do whatever the heck you want to with it. And we're going to see this play out. Yeah, maybe that was a poor choice on myself to just babble about that. Maybe that just makes it seem worse than it's going to be. I think once we start doing some calculations, I think you'll get a better idea of what the bigger picture is.
Yeah, I think so. Thanks.
Yeah. So what I would suggest we do is we're gonna, as we always do in this book or this classes, we're gonna start with. Oh, I just spit in my computer. Every time I do this, my head, it's freaking me out. Let's just start with an old friend. So take the geometric series. So here's what we know. You guys remember this. We know that 1 plus r squared plus r cubed. We know, and if you want to write this in your shorthand, you can. But that's irrelevant right now. What we do know is we know this thing is equal to 1 over 1 minus r. We did this weeks ago. So all I want you to do is I want you to switch out r with x. So just use the letter x. So now it's going to look more like a function. So this creature is equal to this, provided what? When is this true? Of course, what do we need to happen? We need r to be between -1 and 1. That's when this is true. So we need x to be between -1 and 1. So to sort of see how this works, what I'm going to do is I'm going to go to Desmos and I'm going to show you this. And we did this with e and sine and cosine, but now I want to do it with this. So I'm going to show you Desmos. So let's go to, where did it go? Do you guys see Desmos right now?
Yeah.
Yeah, okay. So let's graph this thing. Let's graph y equals 1 divided by 1 minus x. So you should see a red curve here. Let's zoom in a little bit. So 1 over 1 minus x. Now let me start typing this power series. Now I can't type the whole thing because it's infinity. It's forever. But let me do y equals 1 plus x squared plus x cubed plus x to the 4th. What do you see happening? Look at that blue curve I keep graphing. It is taking over the red curve. Now, to be fair, it's not doing it everywhere. It's sticking. Where is it containing itself to? Well, it's containing itself between, if I just restrict myself to -1 and 1, if I restrict myself, ooh, look at that. If I restrict myself between -1 and 1, then that blue curve is pretty much on top of that red curve. Now, you might say, well, I see a gap down here. Well, that's fine. I'll just add more terms and that gap will disappear. So what I'm showing you right now on Desmos is the graphical representation of this. This down here, this algebraic equation. I just showed you what it means graphically on Desmos. So let's play with this equation. Let's manipulate it. Let's have fun with it. So let's replace x with, I don't know, how about negative 4x? So if I start with 1 over 1 minus x, and I know it's equal to this, I'm going to replace, now this is true for x between negative 1 and 1. I'm going to replace x with negative 4x. So that gives me 1 over 1 plus 4x. And then I get 1 minus 4x, and then I have plus 16x squared, and then I have minus 64x cubed. And now this is true when? When will this be true? Well, this is true when negative 4x is less than 1 is less than negative 1. So that might seem silly, but we're going to go back to Desmos in a second. Does anybody have a question about what I just did, though, the algebra?
That's pretty straightforward.
Now let's look at the picture, though. Let's look at the picture instead. If we go back to the picture, if I replace this with plus 4, now we have our red curve. What happens if I start typing in?
You're not on Desmos.
I know, I'm hitting. It keeps running from me, dude. See that now? We there now?
We're there now.
All right, now, so what was the second term? It was 1 minus 4x. And then it was plus 16x squared. And then it was minus 64x cubed. So you'll see now, if I zoom in on this now, the blue one, and by the way, it should be noted, where is this interval of convergence now? We have to be a little more careful. It's not between negative 1 and 1 anymore. It's between negative 2.5 and positive 0.25. So if I zoom in a little bit, you'll see that it's only going to work between negative 2.5 or excuse me, negative 0.25 and positive 0.25. So now I can do the next term. What's the next term? It was going to be the 4th power, so it's 4 to the 4th, x to the 4th. And you see that blue is taking over. Does anybody have a question about this? I can't emphasize enough how important I think it is for you to go on and do this kind of stuff yourself to really get a feel for this. So if you rewrite this, the reason I said that, if you solve this equation, this becomes negative 1/4 less than x less than a 4th. So what I'm saying is, if you start with a power series and you compose it with some linear term, it seems that this makes sense. It seems we created a new power series. So now, what am I doing? I'm representing functions. If you look at the left-hand side of these two equations, what I'm telling you is you can take a function, an old-fashioned function that you used to work with when you were in algebra class. And now I'm telling you, you can write it as a power series. Let's try another thing before we end. Instead of me doing that, let's integrate. Why not? Why not try it? So if I start with 1 over 1 minus x, and I know that this is equal to this, we tried motivating this the last class with you guys with all these derivatives and integrals. Why don't I integrate this thing? Well, what's this become? This becomes negative the natural log of 1 minus x. If you do the integral. And then the right-hand side, integrate each term. You get x plus x squared over 2 plus x cubed over 3 plus x to the 4th over 4. And this goes on forever and ever. And then, of course, we might have our plus c here. And now we've just written the natural log as a power series. Now, of course, you could argue, Daryl, you could say, oh, Grady, this is just hocus pocus. That's, what are you talking about? You're just making crap up. Well, okay, maybe I am, but we could try and look at the graphs and see maybe I'm not making something up. Maybe this could be true. Maybe this manipulation that he did do is in fact logically sound. Maybe it's accurate.
Is that a negative natural log?
Yeah.
Or no?
Do the integral. Yes, it's minus the natural log.
Okay.
So the way I'm getting that, Katie, is I'm doing a U sub in my head. Not in my head. I didn't mean to sound like that, but that, you know, I've done this integral enough. You would probably have to write it down. Yes. Let u be 1 minus x.
Yeah.
And then your du would be negative dx, or negative, or yeah, du is negative dx, and then plug it in. You'll get that. But let's write this thing down. I mean, if you want, let me go up here. Let me replace my red curve with minus the log of 1 minus x. Let me zoom back out. I got this red curve. Now let me put my power series in. What's my power series? It's y equals x plus x squared over 2. I mean, look at this already.
We don't see it.
I know, because I'm going to blow this thing up. Thank you, Darryl. I'm glad you're paying attention, dude. Now you see it, right?
Yep.
But now, when I start adding these terms, I get this black curve, which is going to start taking over the red curve. Now, it's only going to do it between -1 and 1, but that's okay. Actually, I shouldn't say -1 and 1. I'm lying. It's going to be -2. So what you're seeing is you're seeing this thing taking over. Does anybody have any questions about this?
Well, it
Comment?
won't completely take it over.
Well, it won't. What's that? Say that again?
It won't completely take it over.
No,
but
it'll only do it on its interval of convergence. So we'd have to figure out what that interval of convergence is. But we have the pieces for us. If we go back to the whiteboard, first off, if you want to think about what this constant should be, so set x equal to 0. In that case, you get negative log of 1 equals c, and that implies that c has to be 0. That's the first thing you need to know.
Mm-hmm.
And then also, because we started with x being between -1 and 1, we can't expect this to be better outside of it. In fact, it won't be. It's only going to work between -1 and 1. Now, Daryl, you could check the endpoints,
Okay.
and what you'll find is it is going to be true for -2. Excuse me, for -1. It will work for -1. It will converge for -1, and it will diverge for +1. So it's only going to work for certain values. Does that make sense?
Yeah.
And we'll get into the details of this. Well, maybe not the details, but the idea is what I want. We're running out of time. What I want you guys to be able to do is I want you to think about working with power series. I want you to think about differentiate them. Think about this. You know, what we're essentially saying is that any function can really be written as this infinite polynomial. Now that's what we're foreshadowing to. We're sort of, you know, insinuating that, Daryl, you can go out there and you can find any function, and at least on some interval you can write it as an infinite power or an infinite series. And that means that you can differentiate it easy, you can integrate it easy, and we're going to find all kinds of ways we can manipulate this. Does this make any sense? Does anybody have a question or a comment about this? Because I mean, we're kind of getting past time here. So what I think we'll do is we'll end here. Someone's chatting on the chat line. Yeah, Katie, I'll get to you in a second. All right. Any other questions?
Can you go back to the last one?
The last slide? Sure.
Yeah.
This one?
Yeah, I just have to grab something.
Sure. No, don't be afraid to yell. You need me to do something. Does anybody have a question? We good?
Absolutely.
All right. Well, I'm going to stop recording now. Do you?